Okay, so now we're going to try to do some problems with the combined gas law. Now, before we do these, just a reminder, it's always best to pause these videos, try the problems out yourself, and then see how you did. Working through them yourself and struggling through them will help you get them more correct in the future. So don't just watch them. Of course, they'll make sense then. So we've already talked about boils, P1V1 equals P2V2. And we've talked about Charles, where V1 over T1 equals V2 over T2. So what we can do is we can put those two together. We can say, well, if I want to know how pressure, volume, and temperature all work together, I can say PV and T, 1, 1, and 1, equal the PV and T, 2, 2, and 2. And this is always a before, that's not going to work, and an after situation. So you're looking at how does a gas respond before and after you do something to it. So the first problem, you've got a bag of potato chips, and we are packaging that in Denver, or excuse me, it's packaged at sea level where it's 1 atmosphere, has a volume of 315 milliliters. Then we take that bag of chips and we take it to Denver where there's less pressure. What's going to happen to the volume of the bag? So what I want to do is I really want to be intentional about thinking about all these letters and where do the different components go. So 1, 1, 1, 2, 2, 2. So initially the pressure is 1. So over here I'm going to go ahead and write 1 ATM. Initially the volume is 315 milliliters. And initially the temperature doesn't say anything, so I'm just going to put T1. I'm going to write equals. After the fact, when I take it to Denver, it's now going to be 0.775 ATM. And after, it's going, well, we don't know the new volume. That's what we're trying to figure out, V2. And there's no mention of the temperature afterwards either. So here's the first issue. We're using combined gas law, but guess what? It didn't tell us anything about temperature before or after. And since we don't have any information in this problem that tells us what temperature is before or after, we're going to assume it must stay the same. So really, we can get rid of it. So now you look at this, you're like, wait, that's just boils. It is. It's just the Boyle's law problem. I divide this side by 0.775 ATM. Divide this side by 0.775 ATM. These two cancel, and I can just do the math on that, and I get 406.45. Okay, sig figs, there's going to be 3. There's going to be 3 sig figs, so that's going to turn into 406 milliliters. So we did a combined law problem, but it ended up just being boils. Let's try the next one. We're in a submarine. Okay, it's got an internal volume of 11 million liters. Now, that's written out as a word, so we're not even going to worry about sig figs on that. It's got a pressure of 1.25 atmospheres when you're inside there, so it's a little more pressurized than just normal sea level. And one of the crewmen decides to open one of the hatches. Okay, bad idea. So let's go ahead and look at what's going on in this problem. 1, pressure, volume, and temperature. 2. So here's before, here's after. So beforehand it was 1.25 ATM. And beforehand the volume is 11 million liters. It doesn't say anything about temperature again. So here's another one. I'm telling you we're using combined and we don't even have to worry about it. So T1. Afterwards, it doesn't say anything about it. So T2. Okay, so no mention of temperature. We know that they're going to open it where there's a new pressure to be found of 15.75 atmospheres. That's a lot of pressure. And we want to find out what is that new volume of the submarine. Now, good news. If you try to open up the submarine hatch, since there's that pressure on the outside, you probably would not be able to open it. So thankfully you don't kill the whole crew. But if you could open that up, what would happen is that volume of 11 million liters would change drastically. Again, temperatures are canceled. 15.75 here, 15.75 here. That's ATM and ATM. These two guys cancel. And I'm going to do the math on that, and I find out that all of a sudden the volume inside of there, instead of being 11 million, goes down to 873,015 liters, which is way smaller. Okay, that's a big number, but it's way less than 11 million. Sig figs, oh, this one's a doozy. 4 sig figs, 4 sig figs. So this is going to keep 1, 2, 3, and 4. Ooh, it ended on a 0. So to write this out, I'm going to do 873 8.000 liters, and I can put a line there. Or some people might like to do 8.730 times 10 to the 1, 2, 3, 4, 5. 10 to the 5th liters. Either one of those is fine. Those are fine ways to write out that problem. Next, we got a kid with a toy balloon with a volume of 1.8 liters. The temperature of the balloon when it was filled was 20 degrees Celsius and the pressure was 1 atmosphere. The child oh no, this kid's gonna be crying. Okay, they let go of the balloon and it rises to 3 kilometers into the sky where the pressure is 0.667 atmospheres and the temperature is -10. What would the new volume of the balloon? So this is interesting because when I let go of the balloon and the kid starts crying, you're gonna try to figure out the problem. You're gonna say, oh my goodness, when it goes up in the air, there's less pressure. The balloon should expand. But then again, you're going to say, but it's going to be really cold. The balloon should shrink. So pressure says get bigger. Temperature says get smaller. What's going to really happen? So again, I've got to think about this. PVT equals PVT. I've got my 1, 1, 1, my 2, 2, 2, looking at before and after the situation. So remember, beforehand, the pressure is at 1 atmosphere. So I'm going to write 1 ATM. Beforehand, the volume is 1.8 liters. That's a normal size for a balloon, about the size of a 2 liter. Beforehand, the temperature is 20 degrees. Now remember, we can't just put 20 degrees. I got to add that to 273 because I got to turn it into Kelvin. So I have 293 Kelvin. Now again, the little kid lets go of the balloon. They start crying. The balloon rises. This must be a helium balloon. That's why it's rising. Or a hydrogen balloon, which would be dangerous because that could light on fire and cause an explosion. I've never heard of anybody having a hydrogen balloon. Well, we learned about that in Hindenburg. So now we have the new pressure is 0.667 ATM. Pressure is saying, hey, balloon, get bigger. We have the new temperature is -10, so that's going to be 263 Kelvin. And we want to know what is that new volume. Now, algebra. Again, some of you love algebra and you're just going to solve this, but many of you are going to say, I'm not a fan of this. And so if you're not a fan of algebra, here's the stage where things get a little messy. Okay, I'm going to take this number and cross multiply, put it up here. I'm going to take this number and cross multiply and put it here. I'm going to try not to make this too messy. Once I move that up here, I'm going to rewrite this all here. 263K times 1 ATM times 1.80 liters equals, remember this guy is up here now, so this is going to be 293K times 0.667 ATM times V2. Okay, so there's my whole big problem. Now I've got to solve for this V2. So what I'm going to do is I'm going to divide this side by 293K and I'm going to divide this side by 0.667 ATM. And I'm going to do the same on the other side. 293K and 0.667 ATM. Now, order of operations. Oh my goodness, your dear Aunt Sally is going to beat you up if you don't do this one right. You've got to make sure you're using parentheses. What I like to do, personally, I'd take 263 times 1 times 1.80 equals, then I would divide it by 293. I'd press equals, and then I'd divide it by 0.667 equals. That's what I find to be easiest for me when I'm doing these problems. And when I do all that, I'm going to find out that the volume of the balloon, once it does this, this balloon is going to get big. Team pressure wins, 2.422 liters. Sig figs, we're going to change that. Unfortunately, there's only one sig fig there, so 2 liters. The balloon gets bigger. It used to be 1.8, now it's 2 liters. Next, we've got an airliner, has an internal pressure of 1 atmosphere and a temperature of 25 degrees Celsius at takeoff. If the temperature of the airliner drops to 17 degrees during the flight, what is the new cabin pressure? Now I'm going to hold off on drawing this formula. I'm just remember where we're putting things. The original pressure, that's 1.00 ATM. Okay. The original volume of the plane. It doesn't say anything about the volume. Well, let's think about this. Does the volume of the plane, should that change when you're flying? Oh, look, the plane's bigger now. When you go up in the air, does the plane get big? No, the plane should stay the same, but I'm gonna still just put it in there, V1. The original temperature was 25. When I add that to 273, I get 298 Kelvin equals. Now on this other side, what's the new pressure? let's see here. New pressure, that's what we're trying to figure out. What is the new pressure? P2. The new volume, again, remember that hopefully the volume of the airplane is not changing. It's a solid structure. Over top, it's not a balloon. You don't, well, hopefully your airplane isn't made out of a balloon. The new temperature, it is going to be 17, so it's gotten a little colder, so it's 290 K. Now again, remember these two V's? I can cancel those both out. Now I can go ahead and multiply both sides by 290K, 290K, cancel, cancel. And when I go ahead and do the math on this, I get 0.973 ATM. I end up getting 0.97 atmospheres for my official answer with sig figs. Next one, we got divers rising too quickly, causing the bends. That's not a good thing. It's really bad. This is another one of those situations where I haven't given you all the information, and sometimes weird things happen because of that, and you really just have to use the information given to you in the problem. So in this one, it doesn't say anything about temperature at all. Now we know that if you're at the bottom of a lake or bottom of the ocean and you rise up, the temperature is going to change. But they don't tell you that, so we're just going to have to keep it the same. So we know that originally you're at 12.75 ATM, and you are at 15 milliliters of volume. That's the volume of the bubbles in your blood. And you know that you're going to rise up to the surface where it is 1.00 atmospheres. And we want to know what is that new volume of that blood. Now, again, remember, there's a T right here, before and after, but we didn't get any information, so we can just cancel that out. We don't have to worry about it. So now I'm just going to go ahead, and I need to get rid of this 1 atmosphere. So I divide it on this side, and I divide it on this side. Cancel, cancel. I can multiply these three numbers together, and I find out that I have 191.25 milliliters of gas, which with sig figs is 190 milliliters. This is really bad because the bubbles in your blood were 15 milliliters. Now they've expanded to 190, and that can cause paralysis or death. So be very careful when you scuba dive. All right, thanks.